So the motivation here isn't that you necessarily want to be able to change something that's the log base 5 into the log base 2. I mean, that's possible to do, but it's not really that practical or important to do. What you really want to change logs for is so you can calculate what the log base 2 of 15 is, or something like that. So if we look at any log that has an arbitrary base, so log base a of b, that equals the log base c of b divided by the log base c of a. And so the important thing here is that any base, so long as they are the same. So that means that you can use either the natural log or the common log, and then you have two logarithms and a division to make in order to calculate a logarithm in any arbitrary base. So, for example, if I were to calculate the log base 2 of 5, I would take the log of 5 and divide it by the log of 2, or I can take the natural log of 5 divided by the natural log of 2. So what you should do is look on your calculator front and see which is the easier one to do, a natural log or the common log. Sometimes the second function is the natural log, or sometimes the common log is the second function, and sometimes they're both the same. It doesn't matter. So long as you use the same base, you're going to get exactly the same number. So I'd like you to do that pattern and compute those things if you have a calculator. I'm sorry, I guess I should have asked you to bring your calculator, but I see most of you have a calculator.
Okay, since we're going to do it right here.
So you're going to do it right here.
I have not, I need to go through the user's manual. I see there's a base there and I've been dinking
No,
with it.
No, that's not it. Not at all. Okay, put this on pause.
What's the point of this? I don't understand.
It's simply to compute this. If you want to compute this, you want to get a number, this is how you do it with your calculator.
So we're not changing bases, we're just
You are
getting...
Yeah, that's right. You're not, strictly speaking, changing bases.
We are evaluating that.
Mm-hmm.
Okay.
Now, there is a way to change the base here, is that what you do is take this ratio and separate it out to something like this. So if we want to change, let's say, the log base 2 of 5 into the log base 10 of something, and remember this is going to be the log base 10 of 5, and we have the log base 10 of 2. We can do this and so what you get is you're changing bases, and it's kind of useless because this is one number and this is a completely different number. The practicality of this thing is to be able to evaluate this by making use of a base that you know. Okay, so it is possible to change bases, but it's of no practical value. I mean, theoretically it's probably important, but this is the only context that I've ever used it in. Okay? All right. So let's shift gears and talk about graphing logarithmic functions. And remember, we did this with just about every function we've looked at before. Let's say we want to do some transformations. We want to, add a number to x, or we want to add a number to the function. We want to multiply it by a certain number. What does this do, and how can we visualize what this does? Now, the first thing that we want to look at then is some key points. So in this particular function, my base is 2. Now if I take the log base 2 of 2, I get 1, right? So I have one point that I'm always guaranteed. So this is going to be my base, comma 1. And so I have that value into a real nice point right there. The next one is when x equals 1, the log of 1, no matter what base you're in, is going to be 0. So we have this point right there. Now the other thing that that we can't do is take the log of 0. But what 0 tells us is that we have an asymptote at 0. That means we can get really close up to 0. We can calculate the log base 2 of 0.000005. We can get as close as we want to 0, and it'll go, to increasingly more negative numbers. So what we do is we talk about having a vertical asymptote where the log of its argument is 0. So these three facts, if you have an asymptote and you have these 2 points, and then recognize that a log is always increasing, that means it's concave down. There's no point where the concavity changes. Remember where your concavity changed before? You'd have points of inflection. There are no inflection points with the logarithms. And then remember what your domain is. The domain is 0 to infinity, and the range is all numbers. Okay, so anytime you make a transformation or a translation of the log, you're changing its domain, right? Because there are values that you can't take the log of. So if you want to move this graph up or down, back and forth, and all this kind of stuff, that asymptote may change. So our domain changes. So let's look at those transformations explicitly now. All right, so what we had before, and depending on how this is defined, either h, either you have plus h or minus h, but if h is a positive unit here, it moves it right? When you have x minus h, you're moving things to the right. And then it also moves it k units up when you add to the function. You're just adding a constant, so everything moves up by that. I'm sorry, was that too fast? Okay, those are the only 2 things. This is true for any function. So let's look at a logarithmic function. So let's say we have g at x equals the log base 2 of x minus 2 plus 3. So let's think about what's going to happen here if we just look at what I had on the previous slide. So x minus 2. So we expect the graph to move over 2. And so what that means is we no longer have a vertical asymptote at 0. We have a vertical asymptote at 2, right? Because 2 minus 2 is 0. And so if we take the log of x equals 2, or when x equals 2, we get the log of 0. That can't be, so we have a vertical asymptote at 2. And then we expect the whole curve to move up 3. So those points that we had from the intercept and from the base, those things will get adjusted, but they're still easily calculated. So let me show you how that works. Okay, so the vertical asymptote is now x equals 2. Now, the domain of this thing, of course, now is that x minus 2 has to be greater than 0. And so if we solve that, we get x has to be greater than 0. So we know that our entire graph is going to be to the right of that vertical asymptote. Now we got a couple points. Remember, to calculate the point from the intercept, we want to take the log of 1, right? And so what we really want to do is calculate, when does x minus 2 equal 1? Well, that's when x equals 3, right? So if I stick a 3 in here, I'm taking the log of 1, which is just 0. And so then y then equals 0. And so we get the point 3, 3. Yes?
Sorry, can you explain again why it's x minus 2 equals 1 with the 1 part?
Yeah, what we want is to take the logarithm base 2, and we want this expression to equal 1. Because then this whole thing will be 0, and it drops out, then it's just what we add.
Okay.
Okay? So we're choosing that. So that's why we say x minus 2 equals 1 to figure out what x has to be.
Okay.
Okay? All right, that's that point that we got from the intercept before on a normal graph. We also have this point that we get because of the base, right? When we're taking the log base 2 of 2, we're going to get a 1. Okay, so that's an easily computed point. So let's see, when does x minus 2 equal 2? Because we're talking about the base, and so we set x minus 2 equals whatever b is, the base. And so we say, okay, well, that equals 4. We stick 4 in the equation, and so we get the log of 2 of 4 minus 2, which is 2, which is what we intended. So we get 1 plus 3 equals 4. So by coincidence, these turned out to be the same points, or they turned out to be, x and y are the same, 3, 3, and 4, 4. Generally, that it doesn't happen. And in the examples that you'll be working with, it'll be completely different. Okay, so there we have 3 pieces of information. We have the vertical asymptote and we have 2 points. And so when I graph this thing, I put in my vertical asymptote, I plot my 2 points, and then I draw my curve, and I'm done. Anything more precise, you probably need to calculate some other points or whatever, but this at least gives you an impression that this thing goes from negative infinity as x goes to 2 from the right side, and then as x increases, then it goes up into this logarithmic curve. Okay, so let's do a couple other things to it. So when we take a negative x, what we're doing is we're actually, if you want to imagine you've graphed something, if you want to make x negative x, what you do is you turn your piece of paper around and you're looking at it, because then instead of having on your graph, you're looking at 2, when you flip it over this way, you're looking at negative 2. So we're going to make this horizontal reflection, okay, by reflecting in the horizontal direction, so it's about the y-axis. If we multiply x by a factor, we're going to get some compression, right? Because if we're looking at the log of 4, if it's 2 times 2 to get to 4, it's going to happen twice as fast as if we're originally at 2. So we get this compression. If we make our function negative, what we get is that vertical reflection, right? We're just turning our page upside down, where instead of having 100, we're going to have negative 100, and so on. And if we put a coefficient in front of that, we actually get an expansion now, because when we multiply a function by a number, the whole thing gets wider, right? Instead of, if it would normally be, a number like 5, and you multiply by 2, then you get to 10. So it's going to be stretched out. So the thing to remember is that as x changes, the domain changes, and the range of all logarithmic functions remains unchanged. So it's always negative infinity to infinity. But notice here, let's imagine this as being a log function. Before we couldn't take the log of a negative number. Now we really want it to be a negative number, because that's how we get to a positive number. We take a negative negative, right? So let me graph a few of these. Is everybody up with me at this point? Okay, so let's graph this. So we got 3 times the log of negative x plus 1. Now, don't be fooled. Sometimes you see these things written a little more simply, like 1 minus x. Okay, so always, kind of turn those things around in your head. What we're going to expect here is that since we have a plus 1, we're going to be moving that graph left. And since we have a negative x, we're going to make a horizontal reflection, and that 3 is going to stretch it out this way. Okay, so that's a whole lot of visualizing that you can do, and maybe that isn't quite so easy, but let's look at the 3 facts again. We want, did I really say the horizontal asymptote? I mean the vertical asymptote. Okay, writing with my fingers not quite as good as the stylus, but anyway, our vertical asymptote is going to be x equals 1, right? Because we're going to look for that value that makes whatever's inside the parentheses in that log argument, we want that to be 0 to find our asymptote, and so when we solve for x, we get x equals 1. Now the point that's from when we're going to take the log of 1, remember we want to see when does that log, when does this thing in here equal 0? not equals 0, equals 1. So the whole log expression turns out to be 0. We have negative x plus 1 equals 1, and so we have negative x equals 0. And so when x equals 0, we get the log of 1, which is 0, so 0 times 3 is 0, and we end up with this point. And then when it equals 10, remember when we set this argument equal to the base, we have the common log, so that's going to be 10. We find that when x equals 9, negative 9, we get a nice clean 3 out of there. So if we put a negative 9 in here, we get a positive 9, so 9 plus 1 is 10. The common log of 10 is 1. 1 times 3 is 3. So here we have that point. So here's a point that, you know, the x and y aren't equal to each other. We have just some easily calculated values. I mean, nice round whole numbers. Okay, so if I graph this, first thing I do is I write in my vertical asymptote. I put in my point 0, 0. And then I put in my point negative 9 and 3. And really with those 2 points and that asymptote, it tells you what direction things go. So I put my curve in here and it looks like that. And so that's what my graph is going to look like. Remember, when we had a positive x instead of negative x, we have it going from the lower left to the upper right. Here we have it coming from the upper left down to the lower right because of that negative. That was that horizontal reflection. Yeah.
Still not understanding when you the second and third point, the point from negative x plus 1 equals 1. Why are you setting it equal to 1?
Because
Why 10?
what I want to do is I want to make this expression right here.
Yeah.
I want to take the log of 1 because that makes that 0. So that's an easy calculated point. So I'm going to figure out when does minus x plus 1 equal 1.
So it's always going to be 1.
Yeah.
Or you're always going to say equal 1.
Always equals 1 because the log, regardless of the base, of 1 is going to be 0.
Okay.
Now this next one, what you do is you set it equal to the base because if that minus x plus 1 equals 10, then the common log of 10 is going to be 1, and that gives you a nice easy number to calculate again.
So you're always going to use 1 and 10.
Well, 1 in the base.
On the base,
Yeah, and so set it to 0 to find the asymptote, 1 and the base, and those are your three steps. Okay, so time for you to try it. Here I have some graph paper. And you can put these on the same page. I have actually 2 of them, and they don't overlap. So if your graphs cross, you're doing it wrong. And just as a kind of a reminder here, I'll write on the board what the trick is. When we have our log expression, we want this to be equal to 0 for the asymptote. We want it to be equal 1, so the log of 1 equals 0. And then we want to set it to the base, so the log of the base equals 1. Okay, so it's just 3 simple calculations.
what's the first step again?
These three things. So we want to find when the argument in the log, when it's 0 to find your asymptote, where it's 1, so we can calculate the log of 1 equals 0, and then the base, b, so that the log of b equals 1. And this, of course, is log base b of b.
So would, like, you know, the first example is log base 2 and the second one is just log 10? Like, does the basis not matter with, like, the shape of the graph?
It will matter when you're calculating this, and that will determine the shape.
Okay.
In fact, when you look at a family of log curves, you know, let's say the log base 2, log base 3, log base 10, the general shape is all the same. They all go through, when x equals 1, it goes through the axis, and it's just more steep depending on what base you're at.
Okay, so, these two,
Zero.
so anything from log base is
Yeah, log base b of 1 is 0. Right, because the equivalent expression is a to the 0 equals 1.
Yeah.
So log a 1 equals 0.
I'm sorry.
When do we end? At 20 past?
Mm-hmm.
Okay, so I'll give you a couple more minutes. Okay, so let me first calculate those points. And then, I see some of you have either succeeded or not yet. So let's calculate those points. So we want to first find where the asymptote is by setting it equal to 0. And then we set it equal to 1 and its base 2. And so we get these three facts. X equals -3 is the asymptote. -2, -1 is 1 point because -2 plus 3 is 1. So it just turns out to be the -1 from the function here. And then we make it equal to the base, which is 2. And so we find that -1 equals 0 because this will be 1 minus 1, 0. Similarly, if we do that with the next one, we set it to 0, find the asymptote, we set it to 1, which is 0, 3, and then we set it to the base, which is 10, and we end up with -9/2, 2, for that second one. Okay, so I'll put this on a graph. Actually, I had an app do the graph. And so here's the first one. So we have the asymptote was -3, and we had a point of -2 and 1, and we had -1 and 0 right there. So then we can draw the line through it, and we get the curve. The other one, we found the vertical asymptote was 1/2, and we had the points -9/2, 2, and 0, 3, and so there's our points there. So the way the first and the second point works is they will always be at a different level, and so if the one that's further out is lower than the one that's closer into the asymptote, that pretty much dictates the direction of how this goes, of how that curve goes. Okay, this will be posted after class, mid-afternoon or so, if you want to go over it a little bit more carefully. Okay, so this really is very close to just plugging in the points and graphing it. So all the translations and all that, the reflections, you really don't even have to keep track of that. What you really want to do is what happens to the argument of the log. When is it 0, when is it 1, when is it the base? And then you got what you need. Okay, so let's use the rest of the time just to talk about derivatives. And I'm going to blow over this because October 10th we're going to look at this more carefully. But since we're at the end of our logarithmic discussion almost, I want to talk about these from a derivative standpoint. We already established that the derivative of e to the x is e to the x. And that's just a marvelous little fact that will really be quite helpful to us from a calculus standpoint. Okay, so what about the general a to the x? Okay, so let's take the derivative of this. All right, so how are we going to do this? There's no real nice way, but what I'm going to do is I'm going to rewrite it to be e to the log a to the x. Okay, this is one of those things that you had to simplify, and that was based on, x equals e to the log of x. That this is just the function and its inverse, and I'm introducing e right here. And so what I want to do with this now is I'm going to use this x up here and bring it out as a coefficient in front of that. And so I have this. So how do I take the derivative of this now? This is something that's really familiar. This is e to the x times some number, and a is a constant. So we just have a constant times our variable. So we can use the chain rule on this, right? So we take the derivative is the function, the outer function, which is just e to the x. In this case, it's e to the x ln a. And then we take the derivative of x ln a. And so that ln a is a constant. So it's like the derivative of 3x is 3, right? So then by the chain rule, we get that. And then look what I have here. This is exactly that substitution that I made up here. So that's going to be actually a to the x. And I can write that as a to the x ln x, natural log of x. So the derivative of a to the x is going to be a to the x ln x. Now, I'm just offering this as information, kind of closing, our discussion on functions. We'll get back to this when we review the chain rule and all this kind of stuff, and when we start to do calculus on exponentials and logarithms, we'll go back to this. Okay, so let's look at now the derivative of logs. How do we do this? How do we take the derivative of this? So if I first set this up as y equals ln x, I'm going to rewrite that as e to the y equals x. Now we can use that really annoying technique from last semester, implicit differentiation. Because we can take the derivative of e to the y is going to be e to the y, and by chain rule y prime. And then the derivative of x is 1. I'll rearrange this. Now I also know that e to the y equals x, right? So I can make this substitution. The derivative of y is 1 over x. And so we have this marvelous little fact that the derivative of the log of x is just 1 over x. And think about it then, the integral of dx over x is going to be the log of x. Okay, and then the last one, before I let you go, is what about a general log? How do we take the derivative of the log base a of x? We'll restate it like we did before, and we know what the derivative of a to the y is, and then by the chain rule we're going to say the derivative of a to the y is a to the y ln a, and then chain rule says y prime equals 1. And so we'll substitute that original a to the y here. We know that this a to the y is x because that's what we started with. And so we get the derivative is y prime equals 1 over x ln a. And so that's the last of our 4 rules. Okay, and so I'll just summarize them on the next page here. I know, this is really fast, and I'm not going to give you any problems on this yet. I just want to show you that we have derivatives of these things and they're in the forms that are not very nasty. Okay, so of these 4, these 2 are going to be the most important. Okay, that the derivative of e to the x is just e to the x. So if you have e to the y, you can use the chain rule to calculate the derivative there. The derivative of the log is just 1 over x. And then these you probably will have to remind yourself from a table of derivatives. But these 2 are really important, and those are the ones that we're going to return to then. Okay? That's it for today. Now tomorrow what I want you to do